then we have the group all P, or often leave a foot point away, of all pair translations around paths that start and end at P. And all 0 was a set of all pair translations where gamma was non-homotropic. Then Hall 0 was also compact. But not necessarily the whole holonomy group, but we're usually just interested in Hall 0 anyway. Hall 0 is compact. Another fact was that if X and Y are in the tangent space at P, then the curvature endomorphism RXY is an element of the D-adjoint holonomy group. Of course, Hall by definition here sits inside the orthogon group of the tangent space. So this sits inside skew-symmetric matrices of the tangent space. Then we also had the theorem that if, say, if pi r 1 of M is simply connected, then M is a product. Mi is indecomposable. Or equivalently, Hall of Mi acts irreducibly on the tangent space of Mi. And indeed, the splitting came from just the splitting of the holonomic groups. And in addition, Hall of all of M was a product of the holonomic groups. So I'm assuming it's simply connected here. So this means that Hall is equal to Hall 0 in this case. In fact, I'm only going to talk about Hall 0, the holonomic group I don't want to say anything about. So this here meant that one can just reduce the study of holonomic groups to those which come from indecomposable manifold, or equivalent to those that act irreducibly on the tangent space. Right. And then we had a theorem which said that M, let's form a Riemann manifold, right? Hall 0 acts irreducibly on TPM. Let's reform like that. So same thing as M is not a product. If M is simply connected, actually, so for example, one can say that, is that true? Hall 0 of M, I think, is Hall of the universal cover, which is connected. And then the statement was that either M is isometric to a symmetric space, and in fact, remind us, say, if G, K was a symmetric pair with no Euclidean factor, which essentially meant Rn doesn't split off, this implied that Hall 0 is equal to K0. So not only do I know that the manifold is isometric to a symmetric metric, in the usual sense, I also know what the holonomic group is. The holonomic group is K0. And the embedding into the orthogon group of TPM was via the adjoint of K0. So the isotrope representation of homogeneous space. So these we know pretty well now. And then the other case was Hall acts transitively on the sphere radius 1 inside TPM. So one of these possibilities happens. So then I gave you the list of the actions that transitive on the sphere. Let me write them over here. So G contained in the orthogon group. Let's say n plus 1. That means the acts transitively on Sn in Rn plus 1. And Sn is then G mod K. So I write it as a homogeneous space. So I want to give you the list of all homogeneous spaces that act on the sphere. And then the pair G comma K belong to one of the following. So all these are kind of obvious. We discussed most of them before. And then there were the ones coming from exceptional Lie groups. And this is on the 6th sphere. So this is the 6th sphere. Then there was spin 7, mod G2 on S7. And then there was spin 9. Mod spin 7 on S15. So 3 exception cases. So these we've seen, and this we've seen, this maybe not yet, and this we don't need. So there's a maybe proposition here that goes with that. So the third one now says that either it's symmetric space or the holonomy is one of these groups here, one of the G groups. One of these groups here. And I want to discuss each one at a time to see what the geometry is. That's the goal of the next 2 or 3 lectures. If Hol equals SPN times a circle, this implies Hol is equal to SPN. So this case right here, which is a possible way to write the sphere as a homogeneous space, actually is not possible as a holonomic group. If this happens, it's this already. This is possible, but the subgroup inside here is not possible. Or in the sense that then you're this one already. So I can erase it. Okay. From the list of holonomic groups, I can erase this. And then that's actually not so hard. What's not quite as easy, and I actually haven't looked at the proof, is that when I'm in the last case, when it's spin 9, this implies that M is isometric to the symmetric space, Cayley plane, which is F4 mod spin 9, or the dual, in the sense of symmetric spaces, right? For each symmetric, there's a compact symmetric space here, and there's a non-compact dual to that. And so notice here, so this, it fits into this part right here, right? So the claim is F4 spin 9 is a symmetric pair. This then says that, well, if that's the case, spin 9 is a holonomic group. What's the symmetric space? And what this theorem says that if I'm in this category where the holonomic group is spin 9, it's only the Cayley plane. And therefore, I can also drop it in the sense that it fits into the first part, into the symmetric spaces. So although it can occur, it can only occur for this special example. So as far as geometries that one should study, that last one you can also erase, belongs to this one right here. This was, I think, Alfred Gray maybe. I forget who proved that. Not quite so obvious, but I'm not going to do that. Okay, so all the other holonomic groups is something that has very beautiful geometry associated to it. First, notice that in this list here, I claim generically all is equal to SON, since Rxy is inside the holonomic group, and the Lie in the holonomic group. Right? If you have a complicated manifold, then the curvature will be complicated, and if it's complicated enough, it spans the whole orthogonal, the whole Lie algebra of skew-symmetric matrices. And then the holonomic group is a whole orthogonal group, or SON, right? So this implies all equals SON. Remember, for me, Hall is always connected here. I'm just thinking of the simply connected case if you want to. So, of course, quotation mark. Right? I'm not going to make that precise. But certainly, that's a generic case, and everything else is special. So today I want to look at this category right here. So that is supposed to be Kähler geometry. Okay. And then Wednesday or next week, I'll look at the next category. So this year also has a geometry associated, which is called quaternion Kähler. And this here is called hyperkähler. And these are exceptional holonomic groups, which I may get to in the end. Okay, so Kähler geometry, let me explain or remind you what it is. Who knows what a Kähler metric is? You do? Anyone? Do you know what a Kähler metric is? Let me start in the very beginning. So I have a manifold, I have a compact structure. I think I mentioned this before. There's a condition for J to be integrable. So integral means there are local holomorphic charts such that J of a vector is I times a vector. Right, in the sense that it's a complex manifold, so they're coordinate charts. Coordinate interchange are holomorphic. That's what I mean by complex manifold. Once I have that on the tangent space, I then have a unique complex structure. Just give my multiplication by I in local coordinates. And if I can represent J in that form, I say the complex structure is integral. To decide when something is integral, one has, it's called the Ninehouse tensor. I'm not sure if that's the correct spelling, but I think so. There's actually a professor at Penn who invented that, but before my time. And here's a definition, so I can't quite remember it. 1/2 n x y. It's a 2-1 tensor. Let's see. jx jy minus xy minus j jxy minus j xjy. See if the signs are right. Yes. So that's the definition. You have to check it's a tensor. How do you check that? How do you check something as a tensor?
Linear function.
Right. Check its linear order functions. Right. So multiply a function. Of course, this is not linear order functions, but everything's supposed to be cancelled such that it is. Okay. That's a check. And it's a tensor, so defined at every point. And then the Nuremberg, Newland and Nuremberg theorem. says that J is integral if and only if this tensor vanishes. So it's precisely the integrability condition for something to be a complex manifold, for the complex structure to be integral. So I'm not going to prove that. That's not an easy theorem, but I'll use it. Okay, so now I want to put a metric on it also. And then I have to define some kind of compatibility conditions. And there are various levels of compatibility. So here, J is an almost complex structure at the moment. And I say that this the metric is Hermitian, or this triple is Hermitian, or precisely almost Hermitian, if J is an isometry. The simplest kind of condition you could think of as compatibility between the metric and the complex structure. Like it's an isometry. Of course, also, so recall that this implies, so since J squared is equal to minus identity, it implies that J is Q, or Q adjoint. Right? So Jxy is equal to minus xjy. It's equivalent. So I call it almost Hermitian, and I call it Hermitian if J is integral. Okay. That's a fairly weak structure. Of course, give me any complex any complex structure, I claim I can always find a metric, so it acts by isometries. Is that obvious? Let's find a basis that puts J into some kind of normal form. I declare that basis to be orthonormal, because then I have to check it's independent of the normal form. Maybe that's not the best way to do it. There exists a metric so that it's compatible. No. I'm not in the Kähler world yet. I'm only in the Hermitian world right now. So I claim given J, there exists a metric, so it's almost Hermitian.
You choose any metric, fix any metric, and define a new one, put in the metric plus the metric in Jx, Jy.
Okay, let's see what you mean. So choose any metric, then define a new one as what? Like this?
Yeah.
Okay, that's very clever, yes. Now we can check that. That makes J into isometry because J squared is minus identity. Okay, very clever. Okay, so that's not it's just being a complex structure, essentially. Metric always exists. Of course, given the metric that the complex structure exists is a condition. Of course, the manifold must be even dimensional since we have a complex structure. So we're always talking about even dimensional manifolds. If I have such a Hermitian manifold, I can define a true form associated to this, which is the metric with a J put in it. Now notice that this is minus xjy, which is minus jyx, which is minus omega jyx, minus omega yx. So that means omega is a two form on the manifold. So this follows from this compatibility relationship. And also omega is non-degenerate. Also, for example, I can write down a normal, take an orthonormal basis where J is a normal form. Right, so in some orthonormal basis, J has a form 0, identity minus identity. Maybe you put the minus sign there, I forget. And in that form, omega has then is DEI, wedge DEI, plus n. Right, so I can always put omega into the normal form, and then, of course, omega to the n is non-zero. Or if you want even simpler, non-degenerate is clear from this formula also, right? Given y, there must be an x which is non-zero. Well, certainly given x, there must be a y that's non-zero. Jx is non-zero because J is a complex structure. Therefore, I can find a y where it's non-zero. So non-degenerate for omega itself is also clear from the definition. So I always have a non-degenerate 2 form associated with such a Hermitian manifold. So now there's something called omoscalar and scalar, but before I define those things, let me write down the following theorem, which we're going to use to relate various things. So I have a manifold, I have a metric, I have a compatible complex structure, and I have an omega associated to that, so almost Hermitian. And the following are equivalent. So A is d omega is equal to 0, and J is integrable. B is, let's see in what order do I want to do that. There's 4 equivalent conditions. Second one is that nabla J is 0. i.e., so another way to say it is that x parallel implies Jx parallel. Like that's equivalent, so that's maybe formed like this. Equivalently, the complex structure takes parallel vector to parallel vector fields. Equivalently, the holonomic group is contained in the unitary group defined with respect to the complex structure, with respect to the almost complex structure that I have. Because this is defined by a parallel translation, this then implies that this is commutes with J, and therefore it's a complex linear map. So these equivalents are obvious, right? This one is not. Another one is that omega is parallel, and D that all contained in UN. This implies one direction, but the other one we have to think about. So I claim these conditions are equivalent. For this one has to prove the following lemma. So a certain formula, maybe 2 parts. So I can't remember. Name a relationship between the co and derivative of any complex structure compatible with a metric. So that's formula I claim holds. Tedious but straightforward. Another formula, which actually completely general, has nothing to do with Hermitian manifolds, just with Riemannian geometry, that I can compute the exterior derivative of a form in terms of the cohomology derivative of the form. So let's apply to n plus 1 vectors. Right, so omega is the n form on any manifold. I apply to n plus 1 vectors. I look at essentially the cohomology derivative, but of course that's not skew symmetric. So my extra argument, I'm going to put the cohomology derivative here as an extra vector field. When I do that, it's not skew symmetric, so I skew symmetrize. So how do I do that? I multiply here with minus 1 to the I plus 1 nabla xi omega. Now I have n vector fields left over, but I have to remove this one. So this here is a standard notation where you remove xi, right, and plug in the remaining n vectors here. Omega is an n form, so for any k form, say. Well, a k form on n manifold or an n form on something bigger. So maybe k would be a better name, right? So a manifold is usually n-dimensional. So a k form on an n-dimensional manifold. No complex structure now, just a complete general relationship. Have we seen that before?
Yes.
It's a very nice way of...
There are many formulas like that.
Yes.
This one, the covariant derivative, has no bracket terms.
Sure, the standard one is in terms of brackets, yes.
No
right.
financial
Correct. Correct. So, which you can take as a definition of the exterior derivative, right, if you want to. So that's one. The exercise is to show that that standard definition in terms of Lie brackets is the same thing as this in terms of cohomology derivative. That's the exercise. Okay. Have we done that exercise?
Well, by definition, where you have the brackets, you will have this.
It's kind of clear where it should come from. It's for a metric and with a Levi-Zeta connection. So this must be the Levi-Zeta connection of the Riemannian metric. Right? So that's implicit in here. And then there's a relation between brackets and cohomology derivative. That's what it has to be, because it's torsion-free. So that's eventually what it has to boil down to. But I'm not going to do that. So this is an exercise, both of these formulas. Once I have that, I claim the proof of the proposition is easy. So I want to claim they're all equivalent. So A implies B is now obvious, right? Omega closed, J integrable. Then the right-hand side is 0, so J is parallel. And that's A implies B. Why does B imply C? So how was omega defined? Maybe I should put it up here again somewhere. But the implicit was that omega xy is jxy. So you probably know that this formula, right? So the metric is parallel. So if you want in the tensor language, the metric is parallel, right? And of course, we assume that where nabla j is 0. So now you can imagine if you plug that in, you just crank it up. This is parallel, omega must be parallel. Okay. So again, using it's Levi-Zeta.
You don't require
Pardon?
We don't need to consider the negative in the connection. I think we're going to use partial proof.
For which part?
For B.
B implies C?
No, B no,
In here?
Yes.
That could be.
Expand the definition of the
Yeah.
collateral.
That's probably true. Okay, so that's B implies C. Let's do C implies A. So C is nabla omega is 0. So that's our lemma also, right? So nabla omega is equal to 0. Implies by this formula here, d omega 0. And it also has to be integral, and that now follows from part A, right? So now we have d omega is 0, and nabla j is 0, so this implies n is 0. So it's integral also. Right, so all these conclusions are kind of contained in simple consequence of the lemma. For the last part, so let's show that B and D are equivalent for that. So one direction we already saw, right? B implies D. So that's clear. Polynomial is complex linear, power translation is complex linear. The other way around, D implies B, so we know that Hall contained in UN, that's also obvious, right? What does that mean? It means that pair translation commutes with J, right? And that implies that J of a parallel vector field is parallel. Okay, so all of these kind of are easy, assuming the lemma. If either one of those conditions is satisfied, then I say the manifold is scalar. We could do this as Friday as part of the exercise, maybe, just to get your hands dirty on something. So first, maybe I say that our triple, also defines omega, is almost scalar if d omega is equal to 0. So if I have this condition, then I say it's almost scalar, but I don't require its integral yet. That's why it's almost. Right? So d omega is 0, but the complex structure, underlying complex structure, is not yet integrable. And you say it's scalar if any of A or D is satisfied. So any of these conditions says it's scalar. I like this one because it's very geometric, right? Pair translation is an isometry. When J takes pair vector fields to pair vector fields. That's a very nice way of viewing a scalar manifold. There are examples which are almost scalar, not scalar, which are almost summation, not Hermitian. So there it is a difference. But theory of scalar manifold is well developed. Maybe some consequences. This is stronger than saying d omega is 0. Right, so we had this formula, and we remind you d omega was some kind of skew symmetrization of nabla xi omega. So certainly nabla parallel implies d omega 0, but it's stronger. It implies more. Do you know what else it implies? Pardon? Complex structure is integral, yes, sure. That's the only thing on the blackboard, absolutely, but it has other consequences which aren't on the blackboard. You know about harmonic forms, star operator, and delta and d. You know about that kind of stuff?
The concentration is 0.
Yes. So let me remind you a little bit. So d goes from omega k to omega k plus 1. And there's an operator delta, which goes from omega k to omega k minus 1. If I've given a manifold, a metric, and orientation. So this depends on the metric. Isn't defined independently of the metric. Do you know how it's defined? Does anyone remember how it's defined? Have you seen it before? Kind of? There's several definitions. One is you can define it abstractly as some kind of dual of D. So I claim delta is a dual of D. So how do I do it? So just as a formula, so what should that mean? It should mean something like this is if M is compact. I'll define in a minute when M is not compact, where I have an inner product. If I have two K-forms, I have an inner product, which is the integral of the pointwise inner product. Assuming compactness is oriented, so I can integrate. And this puts an inner product on the K-forms. So here omega is in, say, omega k minus 1, and eta is omega k. So this inner product of two K-forms. So omega k minus 1, delta of eta is also k minus 1. This here is on K-forms. That's on k minus 1 forms. Right. So this defines delta formally, at least on a compact manifold. If it's not compact, I can do it a different way. There's something called the star operator, which goes from the pointwise exterior power of the tangent space into lambda n minus k. Remember how that is defined? Again, there's several ways. One is omega wedge star eta is the volume form times, is omega wedge eta times the volume form. Sorry, other way around. Okay, so omega wedge eta is an n form on the manifold, right? I have a well-defined volume form coming from a Macklin orientation, and it must be a multiple of the volume form, and that function is omega wedge star eta. So claim star is a unique operator that satisfies that. And my favorite definition is that star EI1, that's how I compute. Where EI is an oriented orthonormal basis, and these are in order, and these are in order. So that's how you can define an oriented orthonormal basis. So like on a 4-manifold, star of E1 wedge E2 is E3 wedge E4. Star of E1 wedge E3 is minus E2 wedge E4, because the switch the orientation and so on. So then I can find delta in a different way. As what?
There is a sign.
Pardon?
There's a sign, star, G star.
Yes, there's a invariant form, and then there is also a sign form. What's my invariant form? I guess, again, the same thing in the pointwise. Doesn't that make sense? Well, forget the invariant form, but certainly one form is it's equal to star d star with a sign, and the sign is makes the duality work, nk plus n plus 1. And with respect to that, this duality is true. Right? And now there's a formula for delta omega. So it has a Cohen derivative. So what should it look like? So let's say omega is a K form. So I have to apply this to K minus 1 vectors, because it's supposed to be lower the degree. It's a K minus 1 form, and it's a contraction of the Cohen derivative. I think you just put xi in the first variable. See, that makes sense? Omega is a K form, number omega is a K form, so I have to apply it to K vectors. So I do this. And then there's sum over I, and I think there's a sign. Okay, something like this. There's a formula also relating nabla omega to this dual, to the delta operator. As a corollary, you then get that Kähler. Well, that's the same thing as nabla omega is equal to 0. Implies that d omega and delta omega both equal to 0. And then omega is called harmonic. So it's a harmonic form. The Kähler form is a harmonic form. Important consequence. Of course, harmonic comes from the fact that I can define the Laplace operator. And this here implies that Laplace omega is equal to 0. Okay. So another concept of Kähler. This form omega is harmonic. So what's the next thing I want to discuss? Okay. First, some examples. What's my order? 1, 2, 3. Sorry. And then the second holonomic group. most trivial example is Cn, and then the compact one is Cpn. These are the most basic examples of Kähler manifold, and then complex submanifolds of Kähler. Which follows from this interpretation that Kähler meant the form omega is closed. Of course, the restriction form of a closed form is closed, right? And that J is integrable. Closed plus integral implied Kähler. So both of these are clear for complex submanifolds. Particularly, you can look at complex submanifolds in here and here. So algebraic manifolds. These are called Stein manifolds. So you get many, many examples this way. And the other class is Hermitian symmetric spaces. Which I will talk about a little bit later on. These are basic examples of Kähler manifolds. Somehow the name Hermitian is associated with it historically. It's much more than Hermitian, it's really Kähler. So maybe they should be called Kähler symmetric spaces. But they are also very basic examples. Before I get to that, what does it mean for the holonomial group to be contained in SUN? All contained in SUN, if and only if M is Kähler, of course, since it's contained in UN, plus the Ricci curvature is 0. So SUN, actually means Ricci in some sense. Not quite obvious. I want to discuss it in a minute. And these are called Calabi-Yau manifolds. So there's a certain reason for this name. Calabi was the one who suggested some very basic properties of Kähler manifolds, and Yau proved some of them. Maybe I can mention in a minute what something they proved. Hot star is something pointwise, defined in the tangent space. So you can't really expect to relate that to the Cohen derivative. So it's kind of surprising that star d star, which is has very little to do with the metric except for this pointwise operation, has something to do with delta, which has something to do with the Cohen derivative. It's kind of peculiar, right? Okay, to prove this proposition, let's prove the following lemma. So these are properties of being Kähler. So my assumption here is Kähler. One is these are certain compatibilities of the curvature tensor with a complex structure. This one we're going to see is easy. The second one is a little more work. Ricci xy, so it's formula for the Ricci curvature, is summation curvature xjy ei comma jei, where e1 up to en, je1 up to jen is an orthonormal basis. Kind of a funny formula for the Ricci tensor. But as a corollary, we're going to get that Ricci equals 0 implies the complex trace of Rxy is 0, if and only if. But let me get back to that. Let me first prove the lemma, just to see some explicit way of working with the Taylor manifold. So what is Ritchie? Right. So, well, okay. First, this condition right here. What does it say? It says that Rxy is complex linear. That's what it says. Well, but remember that Rxy is an element of the holonomic group, of the holonomic Lie algebra. And we're assuming that it's equal to un. In particular, it's complex linear. Right? So that's just an obvious consequence of things we said about the holonomic group. Part B is a small computation. So what's Ritchie xy? Some of an orthonormal basis. See, my convention is I put it in the middle. First, I take EI. But remember, we have this orthonormal basis given by J of those also, so I have to add to that R JEI XY EI. So now I rewrite this a little bit. Let's see. I claim this is the same thing as R EIX JY JEI. So why is that? Well, first J is an isometry, so I can put it here and here. Then this is complex linear, so I can put it here also. So that's what I did in this step. And here I do something similar. Also, so multiply with J on both sides, then bring it, so that brings it over here. Use complex linear. Pardon? This here? Here? Ah, okay. You're right. Ah, that's what I need. Okay. Very good. I thought that something went wrong. Now I apply J, right? And then I get an EI here. And here I get R of JEI XJY. Okay. Now I want to apply. Pardon? So first I put it here and here. Now use the fact that this here is complex linear by part A to put it in front of the y. Okay. Then do the same thing here. So I did 2 steps in 1 step. Okay. Now let's switch these two. And same thing here. And now I want to use Jacobi identity. And for this, it would be best to reverse this order right here. So now, use Jacobi on the first 3 arguments. So now I think they're in the right order, right? EIX JEI. EIX JEI. So I have to put EI right here. That's how I remember it. Let's see. EIX JEI. With a minus sign, is that right? Or X GI here, X GI here, X in the, yes, and then comma JY. So that's Bianchi identity, right? And now I can switch it around once more. These two and these two. that what we wanted? Where is it? Where is my lemma? Ah, here. X, Y. Up to a sign, I suppose, right? E, I, J. So maybe here's a minus sign. Or I put it over here, right? Doesn't. Right? If I have this here, I can multiply j on both sides, bring it inside, j squared's minus 1, so I can put it either one up to sign. Okay, so these are nice concalations using. So this here uses the whole number group already, right? That's where it comes in. It's complex linear because the whole number group is un. Okay, so that's where the Kähler condition comes in. Now let's see why this implies the interpretation of Ricci flat. A complex trace. We should talk about that in a minute. So I want to relate this to the fact that the whole number group is supposed to be contained in SUN. Right? What's SUN? Skew Hermitian matrix with trace 0, with complex trace 0. Right? Here, this is an operation from Cn to Cn, or R2 into R2, and with complex linear. It's not the real trace, it's a complex trace as a complex matrix. That's what I mean by this here. So this is a real endomorphism, it's complex linear, right? But its trace is certainly 0, because Rxy is skew-symmetric in the real sense. But in the complex sense, it has a trace in general. And the complex trace is the same thing as saying this is 0. So at least my directions are going to go this way.